I say?
So it's a pleasure to welcome our first speaker in connection with the hiring of an assistant professor in astroparticle physics and cosmology. Our first speaker today is Cristiano Germani. He is from, he did his PhD at the, now this is something I...
Portsmouth.
That what?
Portsmouth.
At Portsmouth, yes, with
Roy Martin.
With Roy Martins and company, yes. But then he went was successful in getting a PPARC fellowship after that. So his PhD was of 2003 and stayed at Cambridge for the following 3 years in the group of Hawking's, and then moved on to his fellowship at CISA for the next 2 years between 2006 and 2008, and has been spending 1 year at Meudon Observatoire, and then moved on to the Ludwig LMU, Ludwig Maximilian University in Munich, and that's where he is employed right now since 2010. And we will see how your future will develop, and we wish you all the best. But now let's hear the latest about dark matter, and in particular astrophysical consequences of non-standard gravitational interactions. Please.
Perfect. Thank you very much, Axion. So today I'm going to talk about what I was thinking the last time of my research, which is mainly on cosmology of early time, a little bit of late time cosmology, and I'm going to talk about how this can move to the dark matter side. Okay, so let me start with a kind of, I want to twist a little bit your mind on what you think is inflation. So let me start with something obvious. And what we all know is that if we see the universe at a very large scale, everything looks homogeneous and isotropic, okay? And in particular, also is spatially flat. So this means that spatial distances are measured in Euclidean geometry, okay? But in order to have that, you can imagine that, so this is what is called a Friedmann-Robertson-Walker space-time that is evolving around us. And you can imagine that this is a kind of extremely fine-tuned solution of general relativity. Why? Because, of course, to have something that is exactly homogeneous and isotropic, at least up to its little glitches, then you need to really fine-tune your initial data for the universe. Okay? So in order to solve this very unnatural setup for the beginning, we have a very interesting paradigm, which is called inflation. So let me tell you what I think is inflation. Okay? So inflation is nothing else than you start with something that is completely inhomogeneous and isotropic, so a completely generic initial condition. Okay? So this is like a universe that is very wiggle, and then it stretches very fast. So if you stretch very fast until very wiggle, then at the end you get something homogeneous and isotropic. In other words, our universe is something like you take two distances, like this delta r, some physical distances, and those are stretched away. Oh, can you see they are ready? No? So I take the analogy. So then the two physical distances are stretched in time with some what is called scale factor. Now what we want, as we said, we want a very fast stretching of the universe, which is actually, we say that is an exponential stretching, which is very fast. And then, in other words, what we have is that the Hubble constant, which is nothing else than the scale factor change in time, the velocity of the scale factor change in time is constant. Or, what we will see that is very important, the acceleration of the universe is positive. Okay? So it's expanding, increasing the velocities. So, technically what we say is that the universe is quasi-de Sitter. Alright, so let's see something very simple that we can even understand in Newtonian physics. Now, in Newtonian physics, we know that gravity is attractive, so the acceleration, you know, with Newtonian mechanics, has a minus sign because it's attractive force. Okay, then will depend on the effective energy density of your universe, and since we are in general relativity, also pressure gravitates, and of course we are in 3 dimensions, so we have that the acceleration should be proportional to the energy density plus 3 times the pressure. So inflation means that this acceleration is positive. This means that this guy has to be negative. So rho plus 3p have to be smaller than 0, but when you go out from inflation, it has to be positive. Okay, so far very simple. Now let's see that, in fact, this condition, this innocuous condition or not innocuous, we will see, means that the universe undergoes what is called slow roll. So let me take, okay, so the universe to be homogeneous and isotropic. So the only way to get homogeneity and isotropy is to get a field that is the source of the universe that is itself homogeneous and isotropic. Okay? So for example, we can take a scalar field. The scalar field doesn't have any direction, preferred direction. So this will generically at least be homogeneous and isotropic itself. Okay, so now let's take a potential energy and a kinetic energy of this scalar field. Then we see that the energy density is nothing else than the Hamiltonian of the system, which is nothing else than the kinetic energy plus the potential, and the pressure is nothing else than the Lagrangian, which is the kinetic term minus the potential, as we all know. So then, this guy, rho plus 3p, is nothing else than 2 times minus the potential. So this means that to have inflation, which means this negative, we have to have that the kinetic energy is much smaller than the potential energy. This is what we call in cosmology slow roll. Okay? So in order to have slow roll, I have to have a field that is moving very slow in its potential. And inflation ends when the kinetic energy is the order of the potential. Okay. So now let's again take a little lesson from classical mechanics, and let's see how to make this slow roll. Okay? So take a particle, let me call it phi, which is moving in a resistant medium, like a little ball that is moving into jam, okay, that has some friction. Okay, so this is moving in a resistant medium. So in my equation there will be something proportional to, in some way, the viscosity of the fluid, which is proportional to the velocity of the field. So when friction dominates over the acceleration term, then of course what we have is that a ball that is falling down jam, it's going slower and slower, and then the potential energy takes over. Okay. So this means that in order to have this low roll condition, we really definitely need to have some friction term. Okay? In other words, what we want to have is that the effective equation of motion for this particle is dominated by the friction term, the velocity, and by the pulling force, which is the gradient of the potential. Okay? So that's just classical mechanics. So we just discovered this little different point of view from inflation, that slow roll means to have a high friction. So it means to have a scalar field that is immersed in some resistant medium. Okay? Now general relativity already provides this friction by the expansion of the universe, because when the universe expands and then the scalar field is going down, so it looks like going slower in some way. Okay? And in fact, if you take the Klein-Gordon equation, what you get is that this friction term is 3 times the Hubble constant. Okay, so this is just coming from the usual Klein-Gordon equation. Now the idea is, can I increase this friction without introducing new degrees of freedom? So new fields. Okay, that would be the idea. Okay, so then we have what we call the gravitational enhanced friction mechanism. Basically, I want to increase friction for this scalar field just with gravity, so without introducing new degrees of freedom. And when I say gravity, I really mean a spin 2 particle, massless spin 2 particle. Okay? So this means that I want to, in some way, have the omega squared that has the GR contribution, plus I want to pump it up with some enhanced friction function, which depends generically on the Hubble scale. Why? Because what we know is that friction should not be efficient today, otherwise the galaxy will rip apart if we still are in inflationary scale. Okay? So what we want is that actually the acceleration takes over at late time. So this means when the Hubble constant goes down, because in Friedmann-Robertson-Walker, the only energy scale, if you want, is the Hubble scale. Okay? Of course, the Planck scale as well. So the simplest term you can think of would be, of course, a polynomial and quadratic in h squared over m squared. So until now, I'm just playing a little bit around. Okay? So let me complete the equation of motion. So what I'm saying is that I have this friction, I'm trying to increase with mu factor, and I want to complete the equation of motion. Now one can show that to complete the equation of motion with this mu factor, actually this mu factor has to multiply both the acceleration and the velocity. Why? It's very simple. So let's suppose I was completing the equation of motion with phi double dot and there was a mu here, okay? This would look like, as everybody knows in particle physics, a decaying of the scalar field into other particles, okay? This is just the decaying term. But then this would mean that I'm introducing new degrees of freedom, which I don't want, because I want to create enhanced friction without introducing new degrees of freedom. So I can see this in a slightly different way. So we say that we are in quasi-de Sitter. This means that h dot over h, it's almost zero, because the universe is expanding on almost constant Hubble scale. So what I can do, I can actually rescale time, as you can see, and I will have an effective time for the scalar field by rescaling by the square root of mu. And then I have this condition from the fact that the Hubble constant is very slow. Okay? Now that's very interesting. Then we see that whenever the Hubble scale is much smaller than the scale m, I remind you that this mu is this guy here, so this would mean that mu is much bigger than 1. Then you can see that the effective time, the effective clock of the scale, oops, the effective clock of the scalar field actually is slower and slower with respect to the universe time. So this enhanced friction is doing what, in some sense, what the Hubble scale is doing, but much more efficient. It's telling you that the effective clock of the scalar field is very slow. Okay, so until now, as I said, it was a game, and we tried to do something interesting and enhance the friction, but now we have to make a theory out of that. Okay? So the first thing we all think, when we see something like that, we think that, okay, but the whole system should be boost invariant, at least, because the theory should be Lorentz invariant, the Lagrangian. Okay? So the first thing you would think is that, well, at least you have to rescale all coordinates by the square root of mu, not only the time. Okay? Okay, so let's go there. So we will rescale all these coordinates. But then, this is not enough because I have to make a covariant theory. Okay, so this has to be independent of all coordinate transformation. I'm doing general relativity after all. Okay? And we note the following thing, that the Einstein tensor during inflation is actually of the Sitter type, so it's proportional to the metric by the scale factor h squared. Okay? So you automatically see that in order to get this equation of motion we had before, you have to shift the metric by a term that is a nominal coupling with the Einstein tensor divided by the scale m squared. Okay? And this term is the one that will produce this mu that we had before. Because you can see, I mean, you just plug this one here, you get 1 plus h squared over m squared, which was this term. Okay? Because that's during inflation, of course. Now, the problem is that I promise you that this system only propagates a massless spin 2 and a spin 0, so the infladon and the graviton, and I promise you that there are no any other degrees of freedom, so I have to show you that this is true, okay, in this theory. Well, the first thing you would tell me is that this is true if and only if, first of all the constraints of the theory are satisfied, and second, if there are no higher derivatives, because if there are higher derivatives, then this means I need new initial conditions, so I need new degrees of freedom. So let's see that there are no higher derivatives. And in fact, let's see that this is the unique coupling that can do that. In fact, by Bianchi identities, let's start with the equation of motion for the scalar field. By Bianchi identities, by varying with respect to the scalar field, what happens is that the derivative with respect to the Einstein tensor is transparent. So the divergence of the Einstein tensor is 0. So this means that the equation of motion for the scalar field will only have a square of 2 derivatives. So this means it's not a higher derivative theory in the sense of degrees of freedom. Okay? So that's simple for the scalar field. Now, but then you will tell me, yeah, but still you have to show that even when you vary with respect to the graviton, you don't have higher derivative, and so new degrees of freedom. Also, this one, of course, you can do your brutal force calculation, but there is a very nice shortcut, which is the following. Now, let's go in what is called ADM spacetime, ADM decomposition. ADM decomposition is nothing else than, in general relativity, we all know that everything has to be 4-dimensional, so have to be covariant 4-dimensional, but we can always split our spacetime in time plus space, okay? In a specific way that basically conserves in some way the evolution along time. And this is called ADM. Now, if you do that, in order not to have new degrees of freedom, you need to have in your Lagrangian that the number of derivative has to be equal to the number of field, okay? Or the number of time derivative has to be equal to the number of field, because otherwise you will have higher derivatives. So the danger term in this Lagrange I showed you before is basically GTT is the ADM decomposition phi dot square, okay? So GTT has to be at most one graviton and one time derivative. And this is actually the case because in ADM decomposition, GTT is nothing else than the Hamiltonian of gravity. So the Hamiltonian of gravity is nothing else than one derivative of the spin 2. Okay? So this means that this term is not dangerous and it doesn't produce new degrees of freedom. Okay, so until now then we found a theory that increases this friction and doesn't have new degrees of freedom. However, you may be worried that since we are in early time cosmology, we are at very high energy, so then you may be worried that the whole system violates what is called perturbative unitarity. In other words, we can only trust the theory whenever, in some sense, the energy scale of the theory is much lower some cutoff of the theory. Okay, itself. So the trivial cutoff we have is the Planck scale, of course, because we are in gravity. So we should not ever exceed Planck scale, otherwise we will be in what is called quantum gravity. But then we may have another problem, because I'm introducing a new operator, which is the Einstein tensor divided by this scale here, which is contracted with the scalar. Okay, so this is what is called a non-renormalizable operator. So I cannot do anything to eliminate infinities that are coming from the quantum physics of this term. I have to just cut off a certain scale. So let's see what is the cutoff of this scale. We have to do a checklist. So the usual perturbative unitary, you do the following thing. You expand the fields at linear level. Now you canonically normalize all your field. So remember that now there is a mixing because this has inside the graviton. So what happens is that, and also the scalar field has a different coefficient in front. So you have to recanonically normalize your perturbation of the scalar field by this mass divided by h. Remember that the background for G is the de Sitter. And then you have to usually canonically normalize the gravity. Okay? So we are doing perturbation theory around this Friedmann-Robertson-Walker solution. And then what you find is that this guy, this operator, becomes of order 1 only whenever the Hubble scale are of order m Planck. So in other words, even if I'm introducing a new operator that is not renormalizable, this operator becomes dangerous only at the quantum gravity scale. Okay? Okay, so why bother about all these things? Okay? So the idea is actually to use what we have until now, which is the standard model, and see whether we can do something like inflation, and we'll see later on probably even dark matter, perhaps. Okay, let's start with the finally found Higgs. Okay, so we know we have the Higgs, so we know we have one scalar field, and let's make use of it. Now let's see that the Higgs in the standard model with gravity actually failed to produce inflation. So that's the standard model. Well, it's only the Higgs part, where this is the covariant derivative of the Higgs with gauges, but we don't care during inflation because everything dies off. So covariant derivative becomes just partial. And let me go in the usual unitary gauge, where I keep basically this B, and then we will see that that slow roll means that the Higgs has to go a very high scale, which is basically the Planck scale, so it's much bigger than the electroweak vacuum, so I can completely forget it. Okay, and yeah, so then basically my Lagrangian during inflation looks like just a lambda phi to the 4. Okay, very good. So inflation is telling us that the Hubble scale have to be almost constant, as we said before. Then we see that the acceleration have to be much smaller than the friction in general relativity. And what we have is that this condition automatically implies that the Higgs has to be transplanckian. Okay? So the Higgs field has to be a very large scale. But then if you plug this one into the Ricci scalar, you will find that the Ricci scalar, so your curvature, has to be much bigger than the Planck scale. So the Ricci scalar much bigger than the Planck scale means that you are in the domain of quantum gravity. So this model is completely untrustable. Okay? Because we don't know anything about quantum gravity. Okay. Then let's see what I can do. So let me suppose now instead that at very high energy, actually I can shift the kinetic term of my Higgs by my enhanced friction term. Okay. Then if I do that, again I calculate the slow roll parameter, and I find that the slow roll parameter now is suppressed by this omega term that is much bigger than 1, and before was 1. And then we see that I can easily find that the Ricci scalar is much smaller than the Planck scale, but much bigger than this term, which is much smaller than the Planck scale for large enough omega. So in other words, with enhanced friction mechanism, I can have inflation at sub-Planckian scale and being successful also with the Higgs. Okay, so but you can see that, of course, a low energy regime when the curvature are very small, then the Higgs propagator is canonical, so you will not see any difference at, for example, LHC experiments, because we will see that this guy is over the 10 to the 10 GeV. How do we see that? Well, what we did until now, we made the universe looking like this, okay? Completely boring. But in fact, it looks like that. So this means that, in fact, what we have is that we have a little glitches of inhomogeneity, anisotropies actually, in the temperature fluctuation of the units. And it was just out the 9-year result of WMAP, and they told us that, although they, at least in the abstract, they say that everything is compatible with Gaussianity. So the statistical distribution of the spectrum is Gaussian. Okay, let's keep this one in mind. And let's see how to produce perturbations, how to create this perturbation in the universe. The way is the following. Again, is a background-dependent process. So what we do is we take our scalar field, for example, the Higgs where we were taking. This is the background, and then we claim that there are some quantum fluctuation around it. Now, the two-point correlation function of the temporal fluctuation, average statistical in space, is proportional to the quantum two-point correlation function of the scalar field. And generically, this is different from 0 because this is quantum mechanics. So then, if you match actually these two-point correlation, so the statistic of this two-point correlation function with the statistic of WMAP plus the amplitude of perturbation, you find that this mass scale that the new non-renormalizable operator has to be suppressed is order 10 to the 10 GeV. So as I told you, it's very high and will be only important during inflation, but not at LHC scale. So yeah, basically the Higgs will be GR plus standard model up to and even more LHC scale. Now, as I said, it looks like WMAP is telling us that the universe has a statistic which is Gaussian. Okay. Again, let's see how can we get some information then on these kind of models. Right, so quantum fluctuations in a Friedmann-Robertson-Walker spacetime will depend on what? Will depend on the Hubble scale, of course. Will depend on how different is our background with respect to the zeta. So the epsilon parameter basically telling us how fast is changing the Hubble scale. And of course it will depend also on the sound speed. Because, you know, when you do quantization, what you do is that you are quantizing and you're taking the wave number, which are the gradient of the scalar field, which are multiplied by the sound speed. Okay? Now we are in a non-Lorentz invariant theory. Okay? We are breaking because we are spontaneously breaking by the background with Lorentz. So this means that the CS squared doesn't have to be 1. Okay? It can be different from 1. Now, what you find is that, let's calculate, I mean, this is generic, the endpoint correlation function in Fourier space, and this would be something like some power divided by the CS square, K square. So if we have, for example, the usual Lorentz invariant theory, this guy would be 1, and so this is always proportional to the inverse of momenta. However, in this case, will be always proportional to the sound speed. Okay? So generically, non-trivial nonlinearity in your theory will produce could produce a small CS square. So this would mean that we would have a large non-Gaussianity term. Okay? So in some sense, this model could be very dangerous. Could be very in danger. Because large non-Gaussian spectrum is ruled out by WMAP. Okay. So then, but then you show that by direct computation, actually, the three-point correlation are small in this enhanced friction mechanism. And this was done in this paper. But Let me give you a hint why this is happening very quickly, without doing all the computation. Okay? So that's a simple intuition. What happened is that this whole theory is actually equivalent, it is an expansion of another theory in the following way. Let me do a field definition of the metric. Okay? This is what is called the Finsler metric. So what happened is that I have the metric, and then I shift it with the derivative of the scalar field divided by these two scales, m squared and Planck squared. Okay? I'm just doing this field definition that equal epsilon alpha beta this guy. So what happened is that this whole Lagrangian actually is it's equivalent to this Lagrangian where the Einstein tensor is just the Ricci scalar is on this metric plus order epsilon correction. Now we see that when we are in slow roll this means that this guy is very small because the derivative of the scalar field is very small, and also when we calculate perturbation are also very small. So I can trust, at least during inflation, this expansion. Then we see that in some sense this theory is nothing else, is very close to be just a pure de Sitter with just a massless scalar field. So this would not produce non-Gaussianities because there are no nonlinearities of the scalar, basically. Okay? So that's a quick way to prove that these 3-point correlation functions are not large. Okay. Then, well, there are any specific signatures. Well, the first thing is, of course, and this is all a list of things that is very important to do. Here we have the Higgs. So we have the couplings with all other matter. So basically, in principle, we can have some reheating mechanism that we can really pin down. Okay. Now, the second thing is that after inflation, what happened is that this time, this small epsilon parameter that I had before with this non-trivial field redefinition can actually become smaller than 1, can actually oscillate, because now the nonlinearities can take over. So I don't have anymore this expansion that I gave you before, this guy here, okay? Because now this epsilon can be large. I'm outside inflation, so I'm outside slow roll. Okay, so what happened is that this could produce short-scale instabilities. These short-scale instabilities are actually quite interesting because they can produce actually gravitational collapse of this instability and produce mini black holes. Mini black holes could be also some dark matter candidate. Now, that is a little bit more on the theory side, but what we show is that the kinetic part of the non-minimal, the kinetic non-minimal part of this mechanism can actually be supersymmetrized in a new supergravity context, which is an n equal to 1 to supergravity. And it's new because it was actually used in what is called with new minimal supergravity. But the problem is that still what we did is this supergravitation of this term, but still we have to find a way to find the potential that would produce inflation. But what is more important is that since now we found that this guy can be supersymmetrized, maybe it can also be in string theory. Being in string theory, that could be a very golden pot in some way, because it's very hard until now to find a cosmological solution in string theory, okay? Because usually the potential are too flat or too steep. And then what happened is that instead with this term, even if the potential in string theory are too steep, if there is this new scale that maybe can come from some compactification scale, then we can have that even very steep potential actually works for inflation. Why? Because we basically reduce the kinetic term. Okay? All right, so what did we learn so far? That there is no reason to keep the strong equivalence principle at high energies. In fact, quite the contrary, that the non-minimal couplings are actually quite interesting and can make, for example, the standard model, the Higgs boson standard model to inflate. And but then one may ask, okay, but then if this should be the Higgs, why not the full standard model is non-minimal coupling? Okay. So let's see that, in fact, this would be very interesting for dark matter. Okay, so we go still in every time cosmology, but we are going out from inflation a little bit. We are trying to trade the seeds of the dark matter. So we say that already we may have a micro black hole as instability of this model, and this could be already some dark matter candidate. But it's probably, we can have some other very interesting physics. Now, until now, LHC unfortunately is not showing up any supersymmetric particle. So maybe they are there, probably they are there, because we need that in particle physics, we need new degrees of freedom for a hierarchy problem, for the running of coupling and so forth, so on. But maybe we can still stay in the standard model and think that the axion that should be there to solve the strong CP problem could be a dark matter candidate. Okay? So the dream would be, of course, I just have the standard model and I get inflation and dark matter. That's it. Okay, so let me just give you a short introduction to the strong CP problem and why the axion. So in QCD, one can add a term which is proportional to the FF dual, where this is the Yang-Mills gauge field strength, and we can multiply by a constant. We can add this into the Lagrangian. Why? Because this is a boundary term, so classically doesn't do anything. Okay. However, quantum mechanically, what happens is that this guy gets a beta that is measurable. So if you go into loops, you will see this. In principle, you will see this term. And this term is violating CP. So, but we don't observe it. Okay? So in some way, we have to get rid of this term. So there was this nice idea of Beccher-Quinn, which was the following. Okay, let me suppose I can find some kind of mechanism that transform actually this constant into a field, okay, which we call axion. It's some pseudo Nambu-Goldstone boson, okay, that is suppressed by some scale Fa, where Fa is some scale of spontaneous symmetry breaking. Okay, so what happens is that because now at low energy, FF dual, so this has a beta which is different from 0, I can kind of integrate out, and this will produce automatically a potential for this field. And this potential has a minimum in 0. So there it is, we solved the strong CP problem. Why? Because the only possible solution for this constant that we could have had always is 0. Okay, so that's a very beautiful. And this is, but in order to have that, we have to have this field, which is called the axion. Okay, so let me see how the axion can help us to produce dark matter. I want to be in the case in which I can talk about the axion, meaning that I have to be in the case where the symmetry, where the axion is coming from, is broken. Okay, I don't want to restore the symmetry, otherwise I have to know how the axion was embedded in a high energy theory, which I don't want to at the moment. Okay, so let me be in this case. Okay, during the inflation, we are at energy much higher than the QCD scale, because inflation is, I don't know, 10 to the 14 GeV, for example. And so all these quantum corrections that were producing the axion potential are completely suppressed. So the axion is nothing else than a massless particle. Okay? So the axion value is some kind of randomly distributed from minus pi to pi, because it is an angle, multiplied by this decaying constant. Okay? But then the universe cools down, so you start with some initial angle, okay? And then the universe cools down and produces this potential that I was telling you, that is coming from the quantum correction, the quantum instanton effect of the gauge fields, okay? And this is usually, it's described like a cosine potential. You can see that there is a minimum in 0. This is the one that solves the strong CP problem. Now, what happens is that then at the QCD scale, thanks to the potential, I start from some value, then this guy starts to oscillate, okay? And then this oscillation, this coherent oscillation, is producing actually what is called cold dark matter, because the coherent oscillation looks like dust in an expanding universe. Okay, however, what happens is that during this massless stage, I also produce perturbation, okay? Now, and they likely give some contribution to the temperature fluctuation of the universe, the CMB, this map that we saw before, that we actually don't want, because they are not observed. Okay? So let's see what happened, for example, for an inflationary scale about 10 to the 13 GeV, which is a typical scale of inflation. Then what happened is that if you want to have the right amount of dark matter, I'm not going to bother you with all the formulas, but what you get is that this guy has to be bigger or equal than 10 to the 2 Planck scale. So this means since theta is an angle, you can easily do the mathematics, and you will get that the breaking scale has to be much bigger than the Planck scale. So then you don't trust the axion as dark matter in this model, okay? Because because you have to have some breaking scale, which is again at the quantum gravity regime. In fact, you can see that it's much more complicated. There are some regions where you produce too much gravitational wave, some region where you produce too much dark matter. Some region, so the white region are allowed in the standard picture. This is the inflationary scale, and this is the FA, which is the FA bigger than the inflationary scale. So we see that we could have the axion here. However, here the symmetry of the axion has to be restored. So I need to know a little bit more about UV physics. And I don't want to go in this way, but I would like to go in this way. So you see that usually what happens is that you are right in the middle of producing too much isocurvature perturbation that are forbidden by Planck. Yeah, by WMAP, probably by Planck as well. But. Okay, so then we need the following thing. We need some dynamical effective decaying constant, which is actually much bigger than the Planck scale during inflation, so to kill completely the isocurvature perturbation, and we don't see it into WMAP. But when we go to cold universe, so when we want to have the oscillation, we want that this decaying constant is smaller than the Planck scale. In fact, it's the usual QCD scale, the usual Axion scale. So then, let's see very briefly how to do that. This is just an example, but you don't need what is the axion really, what is the UV scale. But for example, in a Higgs type, the axion is nothing else than the complex scalar field, which is going in some minimum, like the Higgs potential. Okay? And now you see that the axion is nothing else than the canonical normalization of this angle with the VEV of your kind of Higgs term. Okay? So then you remember everything I told you before for the Higgs inflation, and then you see again the trick. You just shift the metric into this new no-minimal coupling that you can do also for the axion. Okay? And then what you will get is that you will get an effective decaying constant that is boosted by this factor of H inflation divided by M. So it's not so the scale of symmetry breaking is still FA, which is sub-Planckian, but there is an effective FA, an effective decaying constant that kills the isocurvature perturbation that are forbidden during inflation. And then you see that when this becomes subdominant, then we have that the FA become much smaller than the Planck scale again, and become in fact, for example, 10 to the 12, 10 to the 13 GeV, which is what we want for dark matter. Okay? Very good. So then what we learned so far is that assume that the scalar, all the scalar in the standard model are non-minimally coupled to gravity in the same way. Then they can both produce inflation and dark matter. Okay. However, many things have to be checked. For example, you have to check the CMB with this dark matter candidate. Why? Because, for example, you have to check whether the coherent oscillation after inflation will be the same. Okay, that's a very important check. Then also the baryon acoustic oscillation, which is basically this wiggle that we have in the WMAP, they may change because what happens is that they depend on the interaction of particles with gravity. Okay, so this is really like an elastic medium. So if I change my Lagrangian, then I will change also the baryon acoustic oscillation. Okay, and this has to be checked with data. And also, of course, from more theoretical side, one has to check whether there are also some quantum gravity correction during inflation. Okay, so the small conclusion is that if you want to construct a theory, the idea is that you tell me what kind of degrees of freedom you want. For example, you tell me you want a scalar field and a graviton, and then I come to you and I give you a Lagrangian. Okay? So now we pass the time in which we wanted to have a renormalizable operator because we know if gravity is not renormalizable. So the only guiding line is the number of degrees of freedom. And in fact, one can find that minimal couplings to the standard model to gravity are only necessary in the infrared limit. This is a very old theorem of Weinberg. Okay? So if you go at very low energies, then the graviton can only couple like general relativity to any particle. Okay, cannot be different. But there is no reason to be the same at ultraviolet, okay, when the energy scale are different. That's why, for example, we can have string theory as well. So, then this is a striking property, and we find is that if we allow that, then the standard model in Axion may account for both inflation and dark matter, which is fantastic. So what about other gauge boson and fermions? Well, for example, they are naturally there whenever you want to, suppose you are in extra dimension and we live in 4 dimension, then we want to localize our field. And what happens is that there is a natural way to make them localize via gravity interaction. And then what happens is that effectively in 4 dimension they will look like they are non-minimally coupled. So there is a lot of phenomenology. For example, you can do what is called gravitational baryogenesis. What does it mean? It means that basically I'm breaking baryon invariance by non-minimally coupling. Why? Because in some sense the conserved charge is not anymore the baryon number, but it's the baryon number multiplied by some curvature. That's more or less the gravitational baryogenesis. So magnetic field can be very interesting, in fact, because if I non-minimally couple the electromagnetic field to gravity, then of course the nonlinear effect of magnetic field can change a lot, especially in gravitational collapse, for example, that they may change completely the fate of a star. Also, in particular, for example, in MHD, and whenever you have actually this nonlinearity effect, like inverse cascade, then you do have probably some important contribution by non-minimal count. Lensing, of course, and as I said before, baryon acoustic consideration. Okay, so let me finish with just a little thing. So I have 3 minutes. And so also gravity can actually non-minimally couple with itself. In some way, it sounds funny, but it's like that. But this is possible only if extra dimensions exist. Why? Because in 4 dimensions, if I want to self-couple gravity, there is a theorem, which is the Lovelock theorem, that is telling me that the only theory that self-coupled to itself is actually a theory that doesn't self, is Einstein theory. Okay, so I cannot have anything else. But if I am at least, for example, in 5 dimensions or something, then I can have terms like Gauss-Bonnet. And these are kind of non-minimally coupling of gravity to itself. Okay? So let me suppose, for example, in the case of brane world, where graviton lives everywhere, and this is a 4-dimensional universe where we live, and all particles lives there. And then what we have a very funny situation. Let me suppose that our universe is this wiggling thing, okay, and is moving in some gravitational potential. In this case, just pictorially a cone, but it could be anything. So now this guy is moving in time in this direction. And what happened is that since we start with some wiggling universe, this guy wants to follow actually the symmetry of the whole space-time. So in some sense, by moving, this guy wants to stretch away. By stretching away, an observer that is living only here will see actually an acceleration, right? Because I take a piece of paper, I stretch it, I'm a little guy, 2-dimensional little guy on top of this, I will see everything going very fast. And in fact, so if the inhomogeneity scale is larger than the Hubble scale, so this is our light cone, our universe is here, okay, then you can find that actually a geometrical interpretation of the acceleration of the universe, which is nothing else than this inhomogeneity scale up to the light cone of the universe, okay? That's why the cosmological constant is dominant, because it's almost at the Hubble scale. And, yeah. Okay, yeah, so possible way to notice this thing, of course, it will change a little bit the CMB. How? Because when we have the CMB, so a signal has to reach us, and have to pass through a little inhomogeneity, arriving to us. This is what is called Sachs-Wolf effect. And of course, if we have a little dishomogeneity, we have to revisit a little bit this little redshift due to the inhomogeneity of the universe. So this could be a way to test this kind of model. Okay, I stop here. Thank you.
Thanks, Cristiano, for an interesting talk. Questions, please. Yes, Ariel.
About you're talking about inflation, so what do you predict for like tensor perturbations on spectral index? Do you have any models?
Yes. So this, as I said, this model with no minimal coupling looks really like the usual single field scenario.
Which I thought was ruled out, wasn't it? Or
The lambda phi to the 4,
Yeah.
yes. The lambda phi to the 4, yeah, but it looks like, in terms of perturbation, looks like the single field scenario, but not in terms of the epsilon parameter. So the slow roll is exactly like single field scenario. So this would be that the gravitational wave are very low actually and cannot be observed now. It can never be observed actually because smaller than 10 to the minus 2. The R, the ratio of scalar to tensor. That's because basically, in order to have this large gravitational wave, you have to have effectively more degrees of freedom, or what is called a small field scenario. But this looks like a large field scenario because effectively, in some sense, the scalar field is Transplanckian. I don't know if I was clear, more or less. Okay, we can discuss later as well.
Other questions? Laura?
Yes, I have one question. There is also another scenario that you probably also know, the one where you couple instead the Higgs known minimally to, to the curvature.
Yeah.
So what are the differences between these two scenarios? Would you be able to distinguish the two?
The way, okay, first of all, philosophically, I would say that if you, what are you doing when you know minimally couple the Ricci scalar? So the thing that Laura was saying is that there is another scenario where what I do is I multiply the Higgs term here, and Planck square, Ricci, and then I do a conformal transformation, and basically this conformal transformation kills the potential. Okay. Now the point philosophically is that this is nothing else than changing the Planck scale in some way. So in some way, I always think that once you give me a theory, meaning giving me a theory means you give me the degrees of freedom in somewhere where the Planck scale is my cutoff scale, is my ultimate cutoff scale. Okay, so it doesn't have to vary in time. So in some way, I want to always be in the Einstein theory philosophy. But let me answer to your question, which is not answering that. This was just a remark. So the other thing is after inflation, is in the coherent oscillation of the inflaton, because the sound speed there is different. Okay, so what happened is that in our case we can have this small instability at small scale, so and can change a little bit this coherent oscillation of the inflaton, and then of course the reheating, because as you know you have to have this coherent oscillation and then this decays into particle. So that is slightly different. Okay, this answers the question, not the first one, but I wanted to remark. So.
Other questions? What about observational signatures of mini black holes, or micro black holes as you call them? Would they be just the evaporation effects?
Oh, that depends on the theory. Well, now this is okay. So what I think is that if the unitary, so if there is no Hawking paradox, okay, then mini black holes are nothing else than long-lived particles, okay, that at some point will decay into other particles, so that there would be like dark matter is decaying into other particles. So they would just look like, actually it would be a kind of bad dark matter because they really only interact gravitationally. Okay, so you have to wait so long time before they decay in something, and of course, then if you believe instead in the Hawking evaporation until the Planck scale and whatever, then these objects cannot are ruled out because they have to produce a huge energy, a huge temperature. But we know that this violates unitarity, so it cannot be. But okay, then we go. Yeah.
Why would that violate unitarity?
Well, unless you have a way to solve the Hawking paradox with the usual semi-classical physics, which you don't.
What are the masses of the primordial black hole?
Well, this I have to see, but the scale. Well, this has to be checked because that depends on. I have to do the numerics, and it seems that it's starting at small scale, but I don't know yet what is the scale, so I cannot answer now to the question. But are not macroscopic.
They're
are not solar masses. Yeah. Are smaller than that.
they're to be still,
About the-
but if they're to be still around, they have to be, I don't know, moon-sized or something like that at least.
10 to 15 grams? I actually
Yeah.
worked on primordial black
Right.
holes. Yeah, that'd be,
right.
Yeah.
So they have to be quite big, otherwise they're gone.
Yeah. Well, it depends on this. Otherwise, they are gone for what? For evaporation, you mean?
Yeah.
Yeah, but that depends. What is your model of evaporation at the end of the? That's what I'm saying. But they could be a moon size. I mean, this is what I don't know. But what I'm saying is that even if they are smaller, then if your model of evaporation is like there is a Hawking evaporation, shrink, and then at some point become just a remnant, particle remnant, then this can look like dark matter, because that's here we are going very theoretical conjecture, everything. So it's, but could be moon size, so we have no problem. It's just that I don't know at the moment because I'm doing now the simulation, so I don't know.
Okay, if there's no further questions, then let's thank Cristiano again.